Hello everyone. So now we are going to see the lecture number 4 in SOM, and we are continuing with the axial deformation. And in this lecture, we will be seeing the stepped bars, tapered bars, and deformation due to self weight. So the axial deformation into stepped, tapered, and due to self weight, we are going to see that. Okay, so let's see till now what we calculated. So we had the general equation, something like, so we had like d del L is nothing but force, right, upon area into modulus of elasticity into dx, right? And then with this, the deformation we calculated by simply integration from 0 to L, and nx, ax, ex into dx. Okay, so here now comes a question that what if this a is not constant? So this ax area is not constant, right? So if it is not constant, that means sometimes it can go something like this taper, right? Here it is this area, here it is this area. So you can see that now what is the we have the area which is not constant. So in that case, let's come to the first thing, which is stepped bars. Okay, so stepped bars are, I hope you can see this, right? So in the stepped bars, we have different segments, and different segments will have different areas, and the E will be like elasticity will be, let's say, that will be different, let's say. Okay, but and it can have same material or different material. So if same material, E will be the same. If different material, E will be the different one, right? So stepped bar with axial load. So for example, we have the this first section, which is of length L1. Area of cross section is A1, right? L is the length, and E1 is its modulus of elasticity. That means the modulus of elasticity is also difference. So in this is uh, introduced by a force P1. Okay, then we have L2. L2 has A2, L2, E2, and it is loaded with the force P2. And then we have a third bar, so which is of A3, L3, and E3, and it is loaded with P3. Okay, so we have three sections, three different bars. Now we need to calculate the internal axial force in each segment. So if I want to calculate the internal axial force, so I'll be just putting a cut here because I want to calculate the force, and that force, let's say, that is N1. Okay, so N1 will be the summation of all external forces on the left side. So external forces on the left side. So in the left side, what is there? So at the left side there is a reaction, Ra, right? So it's nothing but equal to Ra. So the whatever reaction comes on the support, that will be there. Now let's cut the section at here. Okay, so that means this much will come, right? So we have, so P1 was already here, N2, what we are like assuming that N2 is the internal force, and reaction is also there, right? So in this case, so whatever reaction comes, we don't know the direction of that. So N2 will nothing be but the summation of all the forces on the other side. So we have P1, we have Ra1. So don't just worry about the direction of reaction, that will come once we calculate. But in general, we should have that at the left there are these two forces. Then if I put a section here, so at that section I have a force N3, let's say its internal force, and it has these many forces. So reaction plus P1 minus P2. Okay, because P1, P2 direction we know, reactions direction we don't know. So this is how it comes. Okay, so this is the uh, axial force in each of the segment or each of the section. Now we need to calculate the deformation. So deformation due to each of the section will be, so for the first one, first section, the deformation is N1 L1 upon AE, second is N2 L2 upon AE, third is N3 L3 upon AE from PL upon AE formula, right? So in this case, the total deformation will be nothing but, can I change its color? So total deformation will be this. Okay, so total deformation is del 1 plus del 2 plus del 3. So all the deformation, linear algebraic summation of that will give you the total deformation. So I'll add all three, and this is the final answer, del total, right? So this is how we calculate the deformation into stepped bars. Now let's see some sign conventions. So this is a tension positive, compression negative. Okay, so total deformation can be positive, elongation, or it can be negative. It can, if it is elongating, that is positive, and if it is compressing, that means the length is getting short, so it's shortening, and we call it as negative. So the key points are that internal axial force is generally different in each segment, and use the correct area and E for each segment. This we should remember, and apply the superposition and add algebraic deformation. Now this is a direct application of the general formula. This is the general formula. We are just integrating, but here we have a segment, so we just added that. Okay, so this is how we calculate in tapered bar. Right. Now let's see. So we saw everything, like how will we handling the stepped bar. We will be calculating deltas differently, like delta 1, delta 2, delta 3, and we'll add them, right? So final delta will be delta 1 plus delta 2 plus delta 3, right? So this is how we'll handle them. So, and we'll calculate the internal force in each segment, and then we will be having the complete deformation in that. So it comes something like the total algebraic summation, right? So we can generally say that delta will be summation of Ni Li upon Ai Ei, right? And from I, something like that. So this is the stepped bars complete deformation. Okay, now, so the sign convention also we saw, tension positive, compression negative, and then we have stepped versus tapered. So, so here let's say, so in stepped, area like from A1 to A2, it changed, right? From A1, for example, we have, then this is the area till A1, this is the area till A1, this is the area in A2. So in stepped bar, sudden change was there from A1 to A2, right? But this is for stepped. But now we want to see what? We want to see tapered. Now we are moving towards tapered bar. So in tapered bars, we will be seeing that area is a function of x and it's changing continuously. Right? So in tapered bar, area is changing continuously. And in stepped, you will see we are just simply doing summation, and in tapered we will be doing integration because we need a continuous summation. So integration is nothing but continuous summation. right? So this is like a conceptual difference between stepped and taper. Now we'll see a tapered bar. Yeah. So we have tapered bar where area changes continuously along the length. Now geometry of the tapered circular bar will be something like this. Here it is attached to the support or fixed or any support, and here it is and then you are seeing gradually decrease into the diameter. So initially it is d1 and then here it is d2, and p is the force and l is the load. Now the diameters vary linearly from d1 at x is equal to 0 to d2 at x is equal to l, and p is the axial load, that means tension, and e is the Young's modulus, that's constant, right? So P is the axial load which is there on this here, and we are saying that its Young's modulus is E. So it's a homogeneous material, and yeah, so like this we'll be doing. Now can we see the diameter and area as a function of x? Can we do that? Yeah. So if at any section I want to calculate the diameter at any section, let's say it is dx. Okay, so at dx, I want to calculate the diameter. So from the uh, uh, linear interpolation, I can say that dx is nothing but d1 plus d2 minus d1 upon L into x. At what distance we want that? Okay, this is nothing but general linear interpolation. So with that, we got d1 plus d2 minus d1 upon L into x. Okay. Now, what will be the area variation at dx? So, area will be pi by 4 dx square. So, I got the area as well. So, area is pi by 4 d1 plus d2 minus d1 into L upon x square. So, this is something like that. So, and we can see that cross-sectional area is also changing continuously along x. So, this is nothing but the area. Now, I want to calculate the elongation. Okay. And here we have nx, which is p generally. So it was p and it's constant, and e is also constant. It is also not a function of x. There was only dx, and then there was ax, which was a function of x, right? So I wanted to integrate 0 to L. I want to calculate the total deformation, what will be there. So we have 0 to L integration p ax e. Because p and e are constant, which is nx and e, we can take it out, and then can I put pi by 4, so pi upon 4 d1 d2 minus d1, and then we need to simply integrate it. Pi will go out, 4 will go out, and if I want to integrate, this is the something that we want to do. So we will be putting the like rule for integration, and we'll be doing that d1 minus d2. Final answer comes out to be d1 minus d2 into 1 upon d1 minus 1 upon d2. So this is the different the deformation which comes in a tapered bar, and this is intention, right? So it's valid when d1 is not equal to d2. That's what the condition of tapered, right? If it becomes equal, that means it's not tapered and the equation will not be valid. So this is the final deformation of tapered bar, right? Now let's see some special cases. So the special case is if d1 becomes equal to d2. That means bar is something like this. Everywhere constant area. So it's a prismatic bar. We call it prismatic, where area is not changing. So you will be d minus d, 1 minus d. So 0 by 0 form, right? So this becomes 0 by 0 form. And if I take limit, it comes out to be PL upon AE. And A is your pi d square upon 4. So here, so if it becomes 0, that means prismatic bar or uniform bar, for that we already calculated, it comes out to be the same deformation that we calculated, right? And then if d2 becomes 0, that means it is like that much tapered that at the end there is no diameter left, it's just a point left. Okay, so that will be a tapered to a point, right? Tapered to a point, d2 becomes 0, this will be 0, and this will be 0 0, that means 1 minus infinity. So it tends to be like minus infinity. If you are doing anything minus to infinity, it will go up to infinity only, right? So that elongation becomes infinite as the smaller end diameter approaches 0. Okay, so in this case, if you apply load, the deformation will be infinite. If the load is there, deformation will simply go on and go and go on. So these are the two special cases for tapered bars. Now we have some important insight that if we see the area variation, so with the length we see the area variation. So as area decreases, the bar becomes more flexible. You see, as length is increasing, so area is decreasing. It is something like that. So the first insight that came, that as the area increases, the bar becomes more flexible. More area, more flexible. Okay. Now elongation increases if the taper is more severe, like smaller d2. That's what we discussed in case 2. If diameter becomes very smaller, so elongation will increase. Longer the bar, more the elongation. That's it. Higher E, less elongation. More modulus of elasticity, elongation will be less, because it has the quality of elasticity more. That means it can come back to its original shape and size easily, right? And then for the same P and L, smaller d2 gives larger deformation. If you just see this from the equation PL upon AE, you can see smaller d2, larger deformation. Now, other taper shapes for reference. So we have exponential taper. So this is called exponential taper, and this is somewhat parabolic taper. So for exponential taper, I don't think this will be that much important for you, but I have mentioned the formula here. So P upon M AE. So this is what your exponential formula comes out to be, and parabolic taper, if it is there, this is the formula for parabolic taper. Okay. Now, so the tapered bars are continuously, and then we get this formula. So using PL upon AE directly for taper is a common mistake, and it's a very big mistake people do. And not expressing AX correctly, if you are not expressing that, then also your answer will be wrong. And the thing is that you have to like check your units properly. Now, tapered bars are used in structure, machine parts, frame members, transmission towers, and in case where weight optimization is required. Okay, so this is what the tapered bar is. How we'll be calculating the deformation in that? How we'll be getting the uh, like how it is going to used in our daily structures. So yeah, this is for tapered. Now, can we just keep make it back to its original thing? So general taper. So yeah, can we move on to, so the general taper was what? Something that we already saw. In that dx is nothing but d1 plus d2 minus d2 minus d1 upon L into x, right? This is your general taper, and its cross sectional area is ax. So ax is nothing but pi by 4 dx square, right? And then you have to substitute in this equation, and you can calculate the general taper. And then we have linearly tapered circular bar. We saw that. So the first formula that came, that was for linearly tapered circular bar. So now we have important concept, area versus diameter. So in this, can I say that if diameter becomes half, does deformation become twice? So this is a question. So is it possible, like if diameter becomes half, deformation will be twice? So the answer will be no. Why? Because area is directly proportional to diameter square. So if diameter uh, is reducing, right, so you will be seeing that area is also reducing. Okay, so for this we can say area reduces much faster because it's power, right? So if area is reducing, uh, if diameter is reducing, area will reduce much faster. So much faster, that means elongation, deformation will not become twice, it will be more than that, right? So these kind of concepts can come to your exam. Now we come to the self weight. So deformation due to self weight. So if a bar is hanging from support, and no force is there on that, you are not applying any kind of force or any kind of tension or compression, so due to its self weight, will there be deformation? That's what we want to know. So what happens when a bar has its own weight and it's hanging vertically? So can we see that? So axial deformation due to self weight of a bar. So we have the concept, which is like we have a vertical prismatic bar of length L, cross sectional area A, its density rho, and its Young's modulus E. Now bar is fixed at top, okay, fixed, and free at the bottom. If bar deforms due to its own weight, then uh, what we'll be seeing here. So can we see here that, so something like this is the geometry. So we have this fixed support, and from that it's a free end. There is no external force. It's just its weight, and due to gravity, that weight is acting on it. Bottom L and top X is equal to 0. Now we will see at any section X. A, rho and E constant, so that means it's a prismatic bar. So weight of an element. Consider an element of thickness del x. So we saw a thickness del x. Can I know what will be the weight of this del x? So del x will be nothing but, weight is nothing but specific gravity into volume, right? So specific gravity is your rho, and A is specific gravity or density, sorry. Weight is nothing but density into volume, right? Density is nothing but weight upon volume, so weight is density into volume. Density you have given, volume you can calculate. So the cross sectional area into the length. So area into length will give you the volume. So this is volume. So weight comes out to be for this elemental uh, this element. So that is A G uh, into dx. So rho is the density. So okay, this comes out to be mass upon volume is nothing but density, right? So if I want to know weight, so that is density into g into volume, right? So I'll be multiplying g as well here. Okay, then only it gets converted to weight. Now I want to calculate the internal axial force at the section. So at this section I want to calculate the internal axial force. So if I cut the section, let's see the, so gravity is working in this direction, so the force you are assuming is in this direction. So nx is nothing but weight of the portion below that section. So below this section, what will be the weight? That much only is the reaction that is getting generated. So we have from L to X, from L like from X to L or L to X, we can say rho. So weight of the portion below the section. So weight is rho Ag into dx. So below the section, this much weight is there. Now dx is nothing but how much length? That is L minus x. So L minus x. So this is nothing but the force that comes out to be. Now, if I know the force, can I calculate the deformation? So, nx ae into dx. So, nx I kept the value rho ag l minus x, and then dx, and ae. And now we want to know the total elongation. So, total elongation will be 0 to L. And till dx, I want to, so these two a to a cancel, rho into g upon e will go out. Now I have just L minus x into dx. So I'll be just simply doing the integration L into x square minus 2, and then I get do the minus L square upon 2, it will be L square upon 2. So this is the deformation. So it is nothing but rho g L square upon 2. And I know that W is equal to rho A L G, right? If I calculate rho G is nothing but A into like W upon A L. So I want to know rho G. I want to put this rho G here. Okay. So rho G is nothing but W upon AL. So this is W upon AL. So now I want to put this W upon AL here. So I got delta is equal to W upon AL L square upon 2E. This L square to L to L gets cancelled. So we have WL upon 2AE. So you see, you had general deformation was PL upon AE. But if you are seeing this deformation into self weight, so it becomes WL upon 2AE. That means it becomes half of the what was there due to external load. Okay. So this is the relation, like for this you will be having half of the external load. So yeah, now let's see that variation. So the variation comes out to be something like this. Okay. So area under the curve, that will be WL upon 2. Now, physical interpretation: at the top, the section has to carry the entire weight of W of the bar, but at the bottom, free end, there is no weight, right? So, the internal force varies linearly from W to 0. So, the average internal force, so see here, here the force was W, but at L, it should like, I think we should, this is L and it becomes 0, right? So, this is, so what, so this much is the difference from W to 0. So if I take the average, comes out to be W by 2. Hence the elongation becomes half of what was there due to the force, if it was there. So result is valid for uniform prismatic bar. Area cancel out in the expression, this one, and longer bar more elongation, and denser medium more elongation, and like stiffer material less elongation. Okay. So for vertical bars hanging under its own weight, we have half WL upon A, right? So yeah, so this is what we should know about the self weight. So we already discussed that why is the result W upon 2AE, not W upon AE, because at the top there is larger force that this is the section is maintaining, but at the bottom there is no force to maintain, right? So this will be the average, which is half, and then we come out to be, yeah. So with this we come to the end of this lecture, and also we have some questions for you. So these are the questions. Please answer them and tell it into the comment section, and let's see if you guys understood the topic or not. So thank you everyone.